Imagine you are living on the banks of a water body. Opposite to where you live is a huge pharmaceutical unit. Of course, you and your neighbors approved the establishment of such a huge pharmaceutical unit across the water body, assuming that it will improve the livelihood of the people in and around the region. However, as the pharmaceutical unit continues its operation, you observe that the features of the water body begins to change. For one thing, the water becomes more frothy, it emanates some sort of a strange odor, and ultimately it becomes not so potable. You understand that the pharmaceutical units are dumping their waste here, but they have promised you that this waste is rather treated waste. But since your water body is ultimately getting contaminated, you raise it up to the management team of this pharmaceutical unit. Before the day ends, you find that several trucks from Steel Authority Limited begin to dump something that appears to be the waste that gets generated from their own plants, the Steel Authority Limited plants. This essentially enrages you and your neighbors. So, in order to take it up further, you along with your neighbors decide to file a suit, and as a proof of it, the next morning you collect the water from the water body. To your surprise, you find that the frothiness of the water has significantly reduced, the odor has diminished, and it appears to be more potable than yesterday. If this appears to be a mystery to you, if this appears to be some sort of a magic to you, I encourage you to consider what we discussed in our previous session, because we saw the blast furnace slag can be used to treat the pharmaceutical compounds. For example, we have these three different pharmaceutical compounds, and the blast furnace slag has the capability of adsorbing them. Now, in this study, several other cheap adsorbents have been considered, and the list is rather given here. If you look closely, this list essentially comprised either of an engineered material or of a naturally occurring mineral. The blast furnace slag is the only exception, which is a waste material. Now, what we essentially have achieved is using a waste material. Now, it is possible for us to decrease the amount of pharmaceutical compounds in water, which is almost comparable to that of the activated charcoal that gets produced from that of the wood. Now, as opposed to pharmaceutical units, you can also have a textile unit which is contaminating your water body with their dyes. Can blast furnace slag help us in such a context wherein it's not the pharmaceutical units, we are now have water being contaminated by dye that is used to color our textile? Now, solution for this question will be answered towards the end of this session. Now, when blast furnace itself is able to manage several forms of waste that is anthropogenic in nature, why do we have to modify them? So essentially, we modify the blast furnace slag to improve the efficiency with which the blast furnace slag is operating. Either we want to speed up the process at which the blast furnace slag is absorbing the waste material, or we want to use less amount of blast furnace slag to address increased contamination. This is one of the reasons why we modify the blast furnace slag. The other reason is we have seen there are several forms of waste that blast furnace slag can manage, but there can be several different variants of a given waste. So we want to manage different variants of a given waste as well. So in order to do that, we modify the blast furnace slag. So two reasons: improve efficiency and also have a wide range of waste that can be to increase the range of waste that blast furnace slag can manage. Now, one modification that can be done to the blast furnace slag is to oxalate them. So what it essentially means is you are treating your blast furnace slag which is crushed, dried in oxalic acid. This forms a slurry. So once you have the slurry of oxalic acid and the blast furnace slag, you introduce sodium hydroxide, and the blast furnace slag, now potent with oxalic acid, begins to crystallize. And this crystallized blast furnace slag with oxalic acid is what we refer to as oxalated blast furnace slag, and it's referred to as slag ox, some cool name. Now this slag ox or oxalated blast furnace slag efficiently adsorb your cobalt ion. So cobalt, heavy metal, which damages our central nervous system, which causes several types of impairment to humans. So this modified form of blast furnace slag or slag ox can efficiently trap this cobalt ion. Now the source of cobalt ion can be several activities, including mining, but one source that we have not considered in case of a raw blast furnace slag is a nuclear waste. So when we use oxalated blast furnace slag to treat the cobalt ions that generates from that or that is present in the nuclear waste, it is observed that this form of oxalated or modified blast furnace slag can efficiently trap those cobalt ions as well. Now here, as you can see, there is a comparison made between a regular slag and an oxalated slag. Of course, if you are listening, there would be an end semester question on this possibly. So yeah, it could be a cool one. So you see there is a comparison, and it is evident the oxalated or modified blast furnace slag is more efficient in trapping in your cobalt when compared to your raw blast furnace slag. In addition to oxalic acid, aminopropyl group can also be employed to modify your blast furnace slag and increase its efficiency in trapping our lead ion. So similar to that of the cobalt ion, lead ion is also a heavy metal ion that causes severe damage to that of our human body and also the environment it surrounds us. So in order to increase the efficiency with which the blast furnace slag traps this lead ion, we are modifying it now using aminopropyl group. Now one form of this group that we are going to adopt to modify the blast furnace slag is the aminopropyl triethoxysilane. While this is used to modify, aminopropyl trioxysilane is used to modify the blast furnace slag, in order to crystallize it, we will be using essentially ethanol. So in the previous case of modifying it with oxalic acid, sodium hydroxide was used. In this case, ethanol is used in order to crystallize the modified blast furnace slag that is modified through aminopropyl group. The way or the mechanism by which this modified blast furnace slag traps in the lead ion is significantly different from that of course, it's going to be significantly different from that of the original blast furnace slag. That is primarily because there is a drastic change in the chemical composition of this slag. As you can see, of course, there are some visible increase in the composition of the modified blast furnace slag when compared to the raw one. So even though the components remain the same, there is an increase or a decrease in the composition. However, there is one new component that is included in the modified blast furnace slag, that is nitrogen, that comes as a part of the aminopropyl group. And this aminopropyl group is what is responsible for the enhanced trapping of the lead ion. Originally, we relied primarily on, in the case of original blast furnace slag or raw blast furnace slag, we primarily relied on hydroxy groups to trap the lead ions. Now we have the aminopropyl group to trap the lead ions, and this bond that establishes between the aminopropyl group and the lead ions is significantly stronger, so thereby increasing the efficiency with which the lead is trapped by the blast furnace ions. Now one other waste that can be managed by blast furnace slag or by employing blast furnace slag, which we considered in our previous session, is CO2. It was rather an indirect way we were able to reduce the CO2 emission using the blast furnace slag. In that case, we reduced the consumption of cement by replacing some of it with amorphous or glassy blast furnace slag. So indirectly, when we reduce the amount of cement that is being used, we are reducing its production, thereby ultimately reducing the CO2 content. However, cement is not the only CO2 or the source of CO2 emission. We also have the own process of steel making and iron making that generates CO2. So the source of the blast furnace slag is also the source of the CO2 emission. So now what we are going to do is we are going to tackle that CO2 emission as well. So the source of both these are the same, and we are going to tackle one waste with the or using the other waste, which are generated from the same source. You have one waste and another waste generated by the same source. We are going to tackle one using the other. In this case, even though the blast furnace slag is not essentially modified, the way it is deployed is significantly different. So the mechanical properties or the physical nature of the slag is modified in order to use it to trap CO2. So the blast furnace slag remains the same, but now the way it is used is in the form of a fluidized bed. So what you have in this setup is you have a grounded blast furnace slag, and you have a setup that essentially gives us fumes similar to that of ones that gets generated out of any industry. So this fume comprises of CO2, nitrogen, and other gases. So we are stimulating something close to, we are creating something close to fumes that are generated in industries, and we are letting it pass through a filter that primarily comprises of our blast furnace slag, and this filter is shown here. So this filter comprises of blast furnace slag particles which are floating under the velocity of fluid. So these floating blast furnace slag, through which there will be this smoke passing through, and the smoke will trap in the carbon dioxide content. And the reason or the way it is able to do so, it is similar to that, or it is same to that of how it traps the heavy metal ions. So what you essentially observe is there is an interaction between the composition of the blast furnace slag, and this interaction allows for the trapping of the carbon dioxide. Now this primarily stems from the structure of the blast furnace slag. The composition leads to a specific structure, and that structure is responsible for trapping in the carbon dioxide. Now, what we have seen is so far the modified forms of blast furnace slag and the areas wherein it could be deployed. So modification can either be changing its chemical composition, adjusting its chemical content, or by changing its physical features and deploying it in a specific way. Now, it is possible also for us to treat the blast furnace slag as a raw material and then generate or synthesize a new category of materials from it, and ultimately deploying that new category of material into waste management. Now one such new category of material that gets synthesized by using blast furnace slag as a source is LDH, layered double hydroxide. So this new category of the material which is synthesized using blast furnace slag as a raw material comprises of hydroxide layers, as it's shown here, and in between these hydroxide layers you have anions and also water molecules. These hydroxide layers have two metal ions in them, and that is the reason why it is referred to as layer double, because we have two metal ions, we have layer double hydroxides. The source for these metal ions that constitute these hydroxide layers are there can be different sources for it. Now when we use blast furnace slag, we are essentially treating the blast furnace slag as a source of these two different metal ions, and correspondingly we were able to generate such LDHs which are rich in calcium, magnesium and aluminium. So the source of this calcium, magnesium and aluminium are our blast furnace slags. Now in order to generate or synthesize such LDHs which are based or which comprise of rather calcium, magnesium and aluminium, the process begins with the blast furnace slag being treated with hydrochloric acid. So this hydrochloric acid essentially leaches out the metal ions that constitute the LDH, and they tend to dissolve them. And this leached out solution, which is rich in calcium, magnesium and aluminium, is separated out. So what is left of this leached out solution is rich in silica. So you have your blast furnace slag treated with hydrochloric acid. Hydrochloric acid, when treated with a suitable parameter, leaches off the metal ions except for silicon. And if you leave out silicon, all the other metal ions are trapped in this leachate. And this primarily includes calcium, magnesium and aluminium. Now when this leachate is treated with sodium hydroxide, you will crystallize it. Ultimately, under suitable condition, you end up forming the LDHs with the ions, the metal ions from that of the blast furnace slag that has been leached out. When these metal ions are leached out, what essentially we are leaving is a silica rich gel, and that can be used for other purposes as well. So using blast furnace slag, its chemical composition, now we are able to build our layered double hydroxide. And this layered double hydroxide is employed to capture the CO2. Now generally it is the hydroxy group that captures or allows for the capturing of the CO2. Now we do the same because it is in a different way we are deploying this particular group. We have a layered structure with enough space for the carbon dioxide to come and settle in. Now essentially the anion in this case is CO3 2-, and this CO3 2-, it gets replaced with that of carbon dioxide when this LDH is rather employed to filter out or to capture your CO2. So from blast furnace we are generating a new category of materials, blast furnace slag rather. And this new category of material, that is LDH, can be employed to trap the carbon dioxide content that can be generated by any source. Besides carbon dioxide, it is also possible for us to remove the phosphate in any source by using this LDH that is generated from that of the blast furnace slag. The composition of it remains the same, of course, depending on the original composition of the blast furnace slag. The kind of metal ions that are getting leached out vary, but nonetheless when you deploy it for the removal of phosphate, it can notice that it increases the efficiency of it performs well when compared to raw blast furnace slag. So here you have the comparison between raw blast furnace slag, and you have LDH that is generated from the slag, and you have pure LDH. So the key difference between this and this is this LDH is produced from a source that is pristine, and this LDH is produced from the source of that which is nothing but our blast furnace slag. So as you can see, it performs in a better way when compared to the raw blast furnace slag, but even though it's less, it's comparable to that of the pristine LDH. So besides CO2, it is also possible for us to manage the phosphate in the solution. Now, when we consider the formation of this LDH, the technique that is employed to the formation of the LDH, and at the end of the day, when we have this LDH that is rich in metal ions, and when we heat them under a predetermined environment, in a suitable environment, when we heat this LDH, it is possible for us to generate layered double oxide. So what is the composition of the layers now changes. The metal ions still remain the same, but instead of hydroxide, these metal ions are now in the forms of oxide. Now what we essentially have done is we have changed LDH to LDO, so layered double hydroxide is now layered double oxide. Now this layered double oxide can also be employed to absorb our CO2 emission. Now again, essentially, it is the change in the chemical composition that makes this process or this operation of the carbon dioxide absorption by the LDO significantly different from that of the LDH. So essentially the process remains the same. Only difference is we are performing the calcination after the LDH is produced. And this calcination changes the chemical composition or the configuration and ultimately leads to LDO, and it increases the carbon or carbon dioxide adsorption. And as you can see, one advantage of having the layered double oxide in the place of layered double hydroxide is that irrespective of the amount of the LDOs that is being deployed for a given purpose of absorbing the CO2, irrespective of how much we are introducing the LDO in the filter, the efficiency more or less remains the same. Here, as you can see, a different percentage of LDO is deployed in the filters for the carbon dioxide adsorption, and thus the performance more or less remains the same. So ultimately we are achieving a greater absorption with the lesser amount of this kind of materials. So when we change from LDH to LDO, the efficiency increases, and that is the reason why this additional step is taken. Now, one other form of material that is synthesized by using blast furnace slag as the raw material is calcium silicate hydrate. The approach primarily starts with treating the blast furnace slag with the hydrochloric acid. Now, in the previous cases, the parameters were so defined, the experimental parameters were so defined in order to allow the leaching of the metal ions. However, in this case, the leaching is not done, but after treating the blast furnace slag with hydrochloric acid, sodium hydroxide is now introduced to crystallize the blast furnace slag, ultimately giving us calcium silicate hydrate form of the blast furnace slag. Now, this calcium silicate hydrate form of blast furnace slag can be used for trapping in heavy metal ions. Now, originally the heavy metal ions were trapped because of the hydroxy or because of the electrostatic interaction between the heavy metal ions and that of our blast furnace slag. Now what we have done is we have hydrated form of calcium and hydrated form of silica. So when you have the hydrated form of calcium, the bond that establishes between the heavy metal ion and that of the slag CS or calcium silicate hydrate is significantly stronger, thereby increasing the efficiency of the blast furnace slag in trapping the heavy metal ions. So because again we are changing the chemical composition, the efficiency with which the heavy metal ions get trapped in the blast furnace slag also increases. The other form of material that can be generated using blast furnace slag as the source is silica nanomaterial. Now this can also be traced back to the formation of or the synthesis of LDH. Now, if you could recollect, in the synthesis of LDH, we are separating a silica-rich gel from that of the leachate, which is rich in other metal ion. Now, this silica-rich gel can be used to synthesize the silica nanoparticles. So, the way we are treating the silica-rich gel is now in such a way that, or we adopt such an approach that from the silica-rich gel that we separated during the formation of the LDH, we are producing silica nanoparticles, and the rest, instead of translating them or changing them into an LDH, what we have is these siliconized blast furnace slag, and both of these can now be used to manage dyes that gets just thrown away from that of a textile industry. Now, if you could recollect, in the beginning of the session we talked about living opposite to that of a textile industry, and the dyes are getting thrown away from these textile industries, and if you want to treat these dyes, we can use these silica nanoparticle and that of these siliconized blast furnace slag, which are generated from that of the blast furnace waste in order to treat these dyes. Now we are using both the components that gets synthesized from that of the blast furnace slag. Both one is the silica rich gel, which is transformed to that of silica nanoparticles, and the remnant of the silica rich gel. Both are being used to manage or trap in this dye, and as you can see, both of these do an appreciable job in trapping these and decontaminating the water from that of the dye. And besides nanocrystalline nanoparticles of silica, it is also possible for us to use blast furnace slag to synthesize another new category of material, that is activated alkali materials. These activated alkali materials are nothing but an alkali. This essentially needs, or these are synthesized from an alkaline source, and it is treated with high pH solution, thereby activating this alkaline material. So you have a high surface area, high porous source of an alkaline material, and to that you introduce high pH solution. The combination of these gives you activated alkali material. Now, to generate this activated alkali materials, we are using blast furnace slag because of its chemical composition, which we have seen in previous session. Because this blast furnace slag is also alkaline materials, we are using the blast furnace slag as the source for generating or synthesizing this AAM. And of course, this high pH solution remains the same. So this is used as the precursor. So since the blast furnace slag can be viewed as an aluminosilicate precursor for AAMs, to this a high pH solution is introduced in order to activate this alkali materials. Now ultimately, the complex chemical nature of the dye and the chemical groups that are found or that are introduced by this treatment allow for cleansing the water contaminated with dye. So we have seen when the blast furnace slag is modified, its efficiency increases and different variants of waste that it originally managed can be managed. On the other hand, if we use the blast furnace slag as a raw material, different classes of materials can be synthesized from it. One example is activated alkali materials. The other is LDH, LDOs. And other forms of one simple example is nanoparticles of silica. So when we are able to generate such wide or synthesize such wide range of materials, correspondingly the waste managing ability of the blast furnace slag also increases. Now we have seen it is possible for the blast furnace slag in a different form to manage the dyes that are let out of textile industries. So besides the common example of the construction, we have seen the blast furnace slag is used in managing wide range of wastes. Now all these different discussions or the different ways in which the blast furnace slag can be managed, whatever we have seen so far, they are currently being looked into, meaning there are huge scope for potential research in each and every topic that we have discussed so far. And I hope some advancement will be made in this area from one of you who are listening to it. Thank you.